In probability theory, the law of large numbers is a theorem that describes the result of performing the same experiment a large number of times. According to the law, the average of the results obtained from a large number of trials should be close to the expected value and will tend to become closer to the expected value as more trials are performed. The LLN is important because it guarantees stable long-term results for the averages of some random events. For example, while a casino may lose money in a single spin of the roulette wheel, its earnings will tend towards a predictable percentage over a large number of spins. Any winning streak by a player will eventually be overcome by the parameters of the game. It is important to remember that the law only applies as the name indicates when a large number of observations is considered. There is no principle that a small number of observations will coincide with the expected value or that a streak of one value will immediately be balanced by the others. See the gambler's fallacy. According to the law of large numbers, if a large number of six-sided dice are rolled, the average of their values, sometimes called the sample mean, is likely to be close to 3.5, with the precision increasing as more dice are rolled. It follows from the law of large numbers that the empirical probability of success in a series of Bernoulli trials will converge to the theoretical probability. For a Bernoulli random variable, the expected value is the theoretical probability of success, and the average of n such variables, assuming they are independent and identically distributed, is precisely the relative frequency. For example, a fair coin toss is a Bernoulli trial. When a fair coin is flipped once, the theoretical probability that the outcome will be heads is equal to half. Therefore, according to the law of large numbers, the proportion of heads in a large number of coin flips should be roughly half. In particular, the proportion of heads after n flips will almost surely converge to half as n approaches infinity. Although the proportion of heads and tails approaches half, almost surely the absolute difference in the number of heads and tails will become large as the number of flips becomes large. That is, the probability that the absolute difference is a small number approaches zero as the number of flips becomes large. Also, almost surely the ratio of the absolute difference to the number of flips will approach zero. Intuitively, the expected number of heads grows, but at a slower rate than the number of flips, as the number of flips grows. Another good example of the LLN is the Monte Carlo method. These methods are a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. The larger the number of repetitions, the better the approximation tends to be. The reason that this method is important is mainly that, sometimes, it is difficult or impossible to use other approaches. The average of the results obtained from a large number of trials may fail to converge in some cases.
For instance, the average of the results from the Cauchy distribution or some Pareto distributions will not converge as x becomes larger. The reason is heavy tails.
The Cauchy distribution and the Pareto distribution represent two cases. The Cauchy distribution does not have an expectation, whereas the expectation of the Pareto distribution is infinite. Another example is where the random numbers equal the tangent of an angle uniformly distributed between -90 degrees and +90 degrees. The median is zero, but the expected value does not exist, and indeed the average of n such variables has the same distribution as one such variable. It does not converge in probability towards zero or any other value as n goes to infinity. The Italian mathematician Gerolamo Cardano (1501–1576) stated without proof that the accuracies of empirical statistics tend to improve with the number of trials. This was then formalized as a law of large numbers. A special form of the LLN, for a binary random variable, was first proved by Jacob Bernoulli. It took him over 20 years to develop a sufficiently rigorous mathematical proof, which was published in his Ars Conjecturae, The Art of Conjecturing, in 1713. He named this his Golden Theorem, but it became generally known as Bernoulli's theorem. This should not be confused with Bernoulli's principle, named after Jacob Bernoulli's nephew Daniel Bernoulli. In 1837, S.D. Poisson further described it under the name La loi des grands nombres, the law of large numbers. Thereafter, it was known under both names, but the law of large numbers is most frequently used. After Bernoulli and Poisson published their efforts, other mathematicians also contributed to refinement of the law, including Chebyshev, Markov, Borel, Cantelli and Kolmogorov and Khinchin. Markov showed that the law can apply to a random variable that does not have a finite variance under some other weaker assumption, and Khinchin showed in 1929 that if the series consists of independent identically distributed random variables, it suffices that the expected value exists for the weak law of large numbers to be true. These further studies have given rise to two prominent forms of the LLN. One is called the weak law and the other the strong law, in reference to two different modes of convergence of the cumulative sample means to the expected value. In particular, as explained below, the strong form implies the weak. The law of large numbers states that an observed sample average from a large sample will be close to the true population average and that it will get closer the larger the sample. The law of large numbers does not guarantee that a given sample, especially a small sample, will reflect the true population characteristics or that a sample which does not reflect the true population will be balanced by a subsequent sample. In business, the term law of large numbers is sometimes used in a different sense to express the relationship between scale and growth rates. In business, the term law of large numbers is sometimes used in relation to growth rates, stated as a percentage. It suggests that, as a business expands, the percentage rate of growth becomes increasingly difficult to maintain. In business and finance, this term is sometimes used colloquially to refer to the observation that exponential growth rates often do not scale. This is not actually related to the law of large numbers, but may be a result of the law of diminishing marginal returns or diseconomies of scale.